Welcome back to the deep dive. Today, we're diving into something pretty wild. The sheer scale of training modern AI.
Yeah, it's kind of staggering, isn't it?
We're talking models like Llama 4. Training these requires coordinating, get this, over 100,000 GPUs.
And not just in one place either. These are often spread across multiple data centers.
Exactly. And if you, listening right now, are an ML systems engineer, you probably know where this is going. This scale, it breaks things.
Oh, absolutely. Your traditional communication methods, they don't just slow down. They fundamentally fail.
They just hit a brick wall.
Completely. I mean, think about the size of the cluster.
Yeah.
Right? And then add these long network links between different zones or even data centers.
Where the latency can just explode.
Yeah, it can spike like 30 times higher than what you'd see inside a single rack.
Wow.
So every single synchronization step, it becomes this massive performance drain. Catastrophic, really.
Okay, so our mission today is to cut through all that complexity. We're dissecting Meta's answer to this crisis.
That's the NCCLX Collective Communication Framework.
Yep. We've got the deep dive on it, the CTran architecture, the performance numbers, all of it.
Think of this as your shortcut, your inside look at the engineering behind this next-gen, hyperscale distributed ML.
All right, let's start with the villain of the story. That 30x latency spike across data centers.
Right.
Standard libraries, things like baseline NCCL, they were built for high bandwidth, sure, but usually in a low latency setup.
Exactly. Within the rack, or maybe across a few racks.
So when that latency blows up, what exactly inside NCCL starts to, well, buckle?
Okay, so the main flaw, fundamentally, is NCCL's design. It's kernel-driven and, crucially, copy-based.
Copy-based. What does that mean in practice?
It means when a GPU wants to send data, NCCL doesn't just, hand it off to the network card.
Yeah.
No, first, it forces an extra copy, a device-to-device copy, into a temporary buffer, like a FIFO.
Okay.
And then the receiver on the other end, it has to do another copy out of its buffer.
Oh, so 2 extra copies for every transfer. That sounds inefficient.
It is. It seems small, maybe, but that copy operation, it eats up 2 critical, very finite resources.
Let me guess. The resources you actually need for, computing the model.
Precisely. It uses up GPU streaming multiprocessors, the SMs, and maybe even more critically, it consumes high bandwidth memory, HBM bandwidth.
Okay, so communication starts fighting your main compute workload for resources.
Exactly. It becomes a resource contention problem, communication versus computation.
And I imagine that copy-based approach makes the latency problem even worse over those long data center links.
It absolutely does. It creates what you could call a synchronization tax.
Synchronization tax, okay.
Because it's copy-based, the system has to break the data into really small chunks, fine-grained chunking.
Right.
And it needs constant GPU-CPU synchronization at every single stage of the pipeline.
Lots of back and forth chatter.
Tons of it. And when your latency is already high, like across DCs, all that overhead, all those little handshakes, they just kill you. The system basically stalls, waiting for tiny acknowledgments. You can't inject data fast enough to fill the pipe to saturate the bandwidth you actually have.
So you've got the network capacity, but you just can't use it effectively.
You got it. The pipeline keeps stalling.
And you mentioned earlier, beyond just being slow, there's this incompatibility issue, especially with newer dynamic models.
Yes, particularly for inference. Think about mixture of experts models, MOE.
Okay, MOE inference. What breaks there?
That's where the whole data flow kind of falls apart with traditional NCCL. See, NCCL is fundamentally host-initiated.
Meaning the CPU is calling the shots.
Right. Communication arguments like how big the message is, they have to be known up front, statically fixed. And they live on the host CPU.
Okay.
But in MOE, you have this token routing step. The router kernel runs on the GPU, and it decides dynamically where tokens need to go. The send counts are generated on the GPU.
So the information needed for communication isn't on the CPU where NCCL expects it?
Exactly. So you're stuck.
Yeah.
Option 1, copy those dynamic counts back from the GPU to the CPU. Super slow, lots of synchronization, bad idea.
Right.
Option 2, the common workaround. Just tell NCCL to send the maximum possible number of tokens every single time, even if you only need to send a few.
Oh, wow. So you end up sending huge amounts of padding, just wasting.
Massive amounts, just padding zeros or whatever. It wastes bandwidth like crazy and adds latency because you're processing all this useless data.
Okay, that sounds pretty bad. And briefly, what about NVS-HMEM? It's device-initiated, right? Wasn't that an alternative?
It is device-initiated, and it is low latency, which is good, but NVSHMEM has its own big limitation.
Which is?
It needs this special memory region.
Yeah.
Symmetric memory, globally allocated and registered across all the GPUs.
Okay.
The killer is this memory space. It's not shared with PyTorch's main memory manager.
Or fragmentation.
Exactly. You carve out a big chunk of your precious HBM for NVSHMEM, and PyTorch can't use it for your model weights or activations.
So you're making your memory problem worse just to fix communication.
Right. It severely limits how big a model you can actually fit. You just can't build a system at 100K GPU scale that's trying to juggle two totally separate, complex memory systems like that. It doesn't work.
Okay, so it sounds like we really hit a wall. Optimizing latency, optimizing bandwidth, managing memory.
Yeah,
They all started working against each other with the old tools.
we did. A fundamental wall.
So Meta had to rebuild. They created NCCLX, built around something called CTran, the Custom Transport Framework. How does CTran work? What's the core idea?
CTran is really the heart of it, and it's built on a couple of key principles, a sort of new philosophy for collectives.
Okay, principle one.
Host-driven customization. This is a big shift. Instead of having the GPU kernel itself run the whole complex collective algorithm, like NCCL does,
Yeah.
CTran moves that coordination logic, the algorithm state machine, onto a dedicated CPU background thread, one thread per communicator.
Wait, so the CPU thread is orchestrating the collective. What's the GPU doing then?
The GPU side becomes much simpler. It basically just runs a really lightweight stall kernel on the user's CDA stream. It's just there to signal ready or wait.
Okay, but moving complex, potentially latency-sensitive stuff off the GPU onto a CPU thread, doesn't that risk adding new latency? New synchronization points?
That's a really good question, and it's subtle. The win here is control and overlap. Think about complex algorithms like tensor parallelism, fine-grained pipelining.
Right, lots of small steps.
Exactly. That intricate sequencing can now run asynchronously on the CPU background thread. That thread can watch the network state, launch the next transfer, all without constantly interrupting the main GPU compute kernels.
So it enables better overlap between the communication happening in the background and the computation happening on the GPU SMs.
Precisely. You get much finer-grained control over hiding that communication latency behind useful compute.
Okay, that makes sense. And the second core principle, you mentioned it tackles the resource fighting.
Yes, this is probably the biggest paradigm shift. Zero copy and SM-free communication.
Zero copy. Sounds promising.
It really is. The data transfer happens directly from the user's buffer, like the PyTorch tensor memory, straight to the network transport layer.
So no more intermediate FIFO buffers, no extra device-to-device copies.
Gone. Eliminated entirely.
Wow.
And the huge implication is the communication stack itself no longer consumes those precious GPU SMs or eats into your HBM bandwidth for its internal copies.
So communication gets out of the way of computation.
Pretty much. You basically tell the network stack, here's the user tensor, send it, and CTran handles the direct path to the network card.
That zero copy efficiency sounds critical. But if you're just blasting potentially huge messages directly onto the network without those intermediate buffers, isn't there a risk of flooding the network, especially with those different network layers, rack, zone, DC?
Yeah, absolutely. You can't just dump everything at once. Network congestion would kill you. So they needed smart traffic control.
What do they do?
They built something called DQPLB, Dynamic Queue Pair Load Balancing.
DQPLB.
Okay, it's clever. Internally, even though it's zero copy from the user's view, DQPLB partitions that data into smaller segments for transmission. And then it applies rate limiting. It dynamically adjusts how many of these segments are allowed to be in flight on the network at any time based on the type of connection.
So it treats a cross-DC link differently than a link within the same rack.
Exactly. It lets you be aggressive and saturate those high latency, high bandwidth cross-DC links while still being careful not to cause congestion on the shorter, faster links within a zone or rack.
Intelligent traffic shaping for these really complex hierarchical networks.
That's a good way to put it. Adaptive, intelligent traffic management.
Okay, let's talk specifics. How did CTran apply these ideas in practice? Let's start with large-scale training. At 100K GPUs, failures are not an if, they're a when. Fault tolerance is essential, right? Especially for things like hybrid sharding data parallel, HSDP.
Absolutely non-negotiable.
So how did they build the fault-tolerant all-reduce, the FTAR, using CTran?
FTAR was really designed with resource efficiency in mind. Remember, HSTP is already pushing the GPU utilization to the max.
Right, no spare cycles.
So FTAR couldn't be a resource hog. It gets its performance by being really smart about pipelining operations internally. It hides the in-kernel copy and reduction work behind the network RDMA transfers.
And the benchmarks really showed that efficiency, didn't they?
They really did. FTAR gets latency comparable to the baseline NCCL all-reduce, which is already highly optimized. But here's the kicker. FTAR uses only 2 thread blocks on the GPU.
2. How many does NCCL use by default?
NCCL typically defaults to 4, so FTAR uses half the GPU compute resources for the communication operation itself.
And if you make NCCL use only 2 blocks, to compare apples to apples.
The FTAR pulls ahead. It delivers between 9% and 18% lower latency than NCCL when they're both constrained to that same small resource footprint.
So it proves you can have robustness and high performance without wasting GPU resources.
Exactly. It's a leaner, meaner, all-reduce.
Okay, now let's switch gears back to inference and that MOE padding problem we talked about.
Right, the wasted bandwidth.
The solution was these GPU resident collectives, specifically something called all-toll-all-v dynamic. How does reading metadata by reference fix the padding issue?
It fundamentally changes the timing and source of the metadata. Traditional NCCL, remember, reads the metadata, the message sizes by value, when the operation is launched on the CPU host.
Right, using potentially stale or max size information?
But all-toll-all-v dynamic.
Yeah.
It takes the pointer to where that dynamic metadata lives on the GPU specifically, the actual send counts generated by the router kernel. It takes it by reference.
Okay, so it doesn't read the values immediately.
No. The communication kernel, when it's actually ready to run on the GPU, then reads the current values directly from that GPU memory location, just moments before it executes the transfer.
Ah, so it gets the actual up to the millisecond send counts, not some pre-declared maximum.
Precisely. No more guessing, no more sending the maximum possible, just the exact data volume needed for that specific step. It eliminates the padding entirely.
That must be a huge win for bandwidth and efficiency in MOE models.
Massive. Just think of all the bytes not being needlessly shuffled around.
And did they also tackle the raw latency for these kinds of small message operations common in inference?
They did. They focused on reducing the software overhead, often called TRESI for small messages, in all-tall.
How?
A key optimization was getting rid of the explicit control message exchange, that sort of handshake between sender and receiver that NCCL usually does.
That handshake takes time.
A surprising amount. For small messages, that handshake could account for up to 50% half of the total latency.
Wow. How did they get rid of it safely? Don't you need it to make sure the receiver is ready?
They co-designed it with CUDA graphs and used techniques like double buffering for the receive buffers. This guarantees that the receive buffer is ready and safe to write into without needing that explicit back-and-forth network handshake before the data flows.
Clever, leveraging other system features to cut out network chatter.
Exactly. Faster and less network congestion, too.
All right, let's get to the bottom line, the results. For an ML systems engineer managing these huge clusters, what do the numbers say? You mentioned a 12% reduction in training step time.
Yeah, up to 12% reduction in the steady-state training step latency.
On a model that takes weeks or months to train on 100,000 GPUs, 12% faster is, well, it's a lot of money.
It's potentially millions in saved compute costs, absolutely.
Mm.
Plus faster iteration, getting models developed and deployed quicker. It's a huge deal operationally.
And what about getting these massive jobs started? Startup time can be a nightmare, right? Especially with potential node failures during initialization.
That was honestly one of the most impressive results, I think. They really optimized the whole initialization process.
Oh.
Things like optimizing the global process group creation, tackling various CPU-side bottlenecks in setting up the communication world.
And the result?
An 11x faster training startup time at the 96,000 GPU scale.
11 times faster.
Yep. Taking startup from potentially many minutes, where lots can go wrong, down to seconds. That drastically improves the actual useful throughput, the good put, and just makes operating these behemoths much more resilient.
Okay, and did the core zero-copy idea deliver on its promise of raw speed?
It did. The benchmarks for peer-to-peer P2P transfers using CTran zero-copy implementation showed a clear speed-up.
How much?
Compared to the copy-based NCCL P2P, CTran was between 1.09x and 2.7x faster, especially for those medium-sized messages like 1 MB to 128 MB, which are super common in pipeline parallelism.
So nearly 3x faster in some cases, just by cutting out the copies.
Exactly. It really validates that core architectural decision.
And for inference, did the GPU resident collectives pay off?
Definitely. Across different distributed inference setups, they measured end-to-end decoding latency improvements ranging from 15% all the way up to 80%.
80%?
Yeah, huge gains, confirming that reading dynamic metadata directly from the GPU works It makes a massive difference in real-world scenarios like MOE.
Okay, this all sounds great architecturally, great benchmark results. But let's talk practicalities.
The how-tos.
Yeah. For the ML engineer listening, maybe writing PyTorch code, who wants to actually use NCCLX and get these benefits, what changes? CTran needs zero copy, right?
Yeah.
And zero copy means you have to somehow tell the network layer about the memory buffer before you use it, registering the memory.
Correct. You need to register the user buffer with the network hardware. Basically pinning it so the NIC can access it directly via RDMA.
Doesn't that clash horribly with how PyTorch manages memory? PyTorch likes to allocate, deallocate, reuse memory under the hood pretty dynamically.
It clashes significantly. That's the core challenge of integrating zero copy into a framework like PyTorch that abstracts memory management away from the user.
What happens if you just try to register every buffer right before you use it?
Bad things. That registration process itself can be slow. It involves interacting with the CDDA driver, and there can be contention. We're talking potential latency spikes of up to 100 milliseconds just for the registration step.
Ouch! 100 meters pause would kill performance gains.
Completely, so you can't just register naively every time.
So how does the engineer actually bridge this gap? How do they get zero copy working with PyTorch without these massive latency spikes?
NCCLX offers two main ways to handle this, and you, the engineer, have to choose based on your workload's needs. It's a trade-off.
Okay, option one. Let's start with the one that sounds easier, maybe more transparent.
That would be auto-registration, sometimes called lazy registration.
Simply registration. Okay.
The idea here is it's mostly transparent to your PyTorch script. NCCLX hooks into PyTorch's allocator. It tracks the memory segments CEDA uses, and it caches them. It only actually registers a buffer with the network layer the very first time it's used for a CTran zero-copy communication operation.
Ah, so it delays the registration costs until the first use.
Exactly. And if your training script reuses the same communication buffers over and over again across training steps, which is pretty common, then this works well. The registration cost gets paid once, upfront, and then amortized over many uses.
How do you turn it on?
Simple environment variable. You set torch exclusions the regicator hook to 1.
Okay. Sounds convenient. What's the catch?
The catch is you still might hit that registration latency spike on the very first use of a new buffer. If your workload allocates lots of new short-lived buffers for communication, this might not be ideal.
Right. So what's the alternative? For workloads where you absolutely need predictable, minimal latency, maybe like pipeline parallelism.
For those cases, there's the memory pool mode.
Memory pool. Less transparent, I assume.
Much less transparent, but more predictable. The idea here is you pre-allocate a large chunk of GPU memory specifically for communication at initialization time.
Okay.
And critically, you register this entire pool with the network layer up front, once.
Ah, so all the memory that will be used for zero-copy communication is registered before the main training loop even starts.
Precisely. So during runtime, when you need a buffer for communication, you allocate it from this pre-registered pool. Since it's already registered, there's no registration overhead, no latency spikes during the actual communication step.
Guaranteed low latency communication stability.
That's the benefit. You get predictable performance.
But the trade-off sounds significant. You have to manage this separate pool.
Yes. You have to explicitly tell PyTorch, allocate this tensor for communication from the registered pool. It complicates your memory management code.
Yeah.
You need a tag or label tensors destined for zero-copy communication.
So more work for the engineer, but guarantees speed.
That's the trade-off.
Yeah.
Transparency and potential first-use latency spikes with auto-registration versus explicit management and guaranteed low latency with the memory pool.
Wow. Okay, so stepping back, this whole NCCLX CTran effort, it's really a fundamental shift, isn't it?
It really is.
Moving away from these older kernel-driven, copy-based approaches that introduce latency and fight for resources.
Towards this host-driven zero-copy architecture. Highly optimized, customizable, and crucially, built to be fault-tolerant at that insane 100K GPU scale.
It's fascinating how they tackled the problems at each layer.
And that memory pool mode, the one that gives you the guaranteed low latency, it highlights a really interesting tension.
How so?
Well, it solves the communication registration bottleneck by pre-allocating and registering that dedicated pool of HBM.
Right.
But that memory in the pool, it's now only for communication. It can't be used by PyTorch for your actual model weights activations or optimizer states.
Ah, so you're carving out precious HBM just for communication buffers.
Exactly. And in the world of large language models, you're always hungry for more HBM. You're always right on the edge of fitting the model itself.
That's a constant battle, fitting everything into memory.
It is. So this leads to a really practical but tricky panel question for you, the ML systems engineer listening. When you're deploying these massive HBM-hungry models, and you choose the memory pool mode for communication performance, how do you decide how big to make that pool?
Right. Too small. And maybe your communication patterns don't fit. Too big.
Too big, and you might steal just enough HBM that your main model weights no longer fit. You trigger an out-of-memory error, an O.
Ah, the dreaded O.
Exactly.
Yeah.
So how do you mathematically model that trade-off? How do you predict the optimal size for that communication memory pool to maximize your network efficiency without accidentally ohming your giant model?
That balancing act, finding the sweet spot between communication speed and having enough memory for the model itself.
That tightrope walk, that's really the sharp end of hyperscale systems engineering right now, something to definitely think about.